Hello everyone, today I'll introduce our work, PAMotion. Humans often manipulate multiple objects in daily life, which makes multi-object interactions inherently complex. Existing methods for generating these interactions often produce unrealistic artifacts. Two common issues are penetration and float. In addition, high-level action goals from instructions can conflict with the detailed hand motions required for physical plausibility, making it challenging to generate realistic human-object interactions. Next, let's talk about the motivation behind our physics-aware modeling. Our physics-aware modeling is driven by the observation that an object's acceleration indicates its contact state. We classify this into three states. Free motion acceleration aligns with gravity, static contact zero acceleration, and contact motion acceleration deviates from gravity. Modeling these states ensures physical consistency in motion generation, preventing artifacts like floating or penetration. The goal of PAMotion is to generate physically consistent full-body interactions with multiple objects. There are two key components in our framework: physics-aware interaction loss, which enforces both dynamic and geometric constraints. Course-defined generation strategy, which generates motion into stages. Now let's take a look at our physics-aware motion modeling. The key idea is that an object's acceleration indicates whether it is in contact with the human or other objects. We divide motion into three states. Free motion state: the object's acceleration is roughly equal to gravity, like during free fall. In this case, there's no contact, so the loss is near zero. Static contact state: the object is held stationary and forces balance, so acceleration is zero. Contact motion state: the object is being actively manipulated, with acceleration deviating from gravity. Now, let's focus on the hand-object distance dt, which is critical in this loss. We introduce a hyperparameter beta, representing the ideal contact distance, which we set to 0.01 in our experiments. When dt greater than beta, the object is slightly detached from the hand, which we call floating. As the distance increases, the loss increases gradually, softly encouraging the object to move closer to the hand. When dt less than beta, the hand penetrates the object. In this case, the loss rises sharply as penetration depth increases, strongly penalizing unrealistic interpenetration. This design allows the loss to softly supervise floating while heavily penalizing penetration, and the dynamic weight ensures it only applies when physically meaningful, that is, during actual contact or manipulation. Overall, loss physics couples object acceleration with hand-object distance, guiding the model to generate physically plausible full-body interactions, avoiding floating and penetration, while still allowing unconstrained motion in free motion states. Next, I'll introduce our course-defined generation strategy, which utilizes a two-stage conditional diffusion model. Stage 1, coarse global interaction. We predict global human motion and object translations using a dual-branch diffusion network, conditioned on initial states, BPS object geometry, and clip text embeddings. This stage is supervised by kinematic and geometric losses to capture text-aligned global motions and stable spatial relationships. Stage 2, fine-grained physical interact tie-in. Conditioned on the course outputs, we refine hand articulation and object rotations. Crucially, we introduce a physics-aware interaction loss computed via object acceleration to enforce physical supervision. In summary, PAMotion balances task alignment with physical realism by first generating goal-aligned global motion, and then refining physically consistent hand-object contacts. Here are our quantitative results on the HEMO dataset. Compared to recent baselines like prior MDM and HEMO-Gen, our method achieves the best performance across almost all metrics. Furthermore, the bottom tables show our ablation study. They clearly verify that our proposed loss is the primary driver for improving both motion text alignment and physical realism. Here we visually compare PAMotion with the state-of-the-art baseline. While the baseline frequently generates physically impossible hand-object intersections, or mid-air floating. Our method effortlessly handles these complex multi-object scenarios. Thank you all for your time and attention.